some bases. Okay, we're looking at, we left off actually right before this, talking about Bronsted acid-base reactions. Now this is an example of Bronsted acid-base reaction or Lewis acid-base reaction. This one's called the auto-ionization or the ionization of water. So if we take two water molecules, they can react with each other. One water molecule acts as the base and fluxes a proton off, leaving the electrons behind there. What that's going to form is hydronium. And hydroxide. All right, is there a driving force for this reaction? If you look at it, not really much of a driving force. We're going from, this will be our base or acid here. This will be our base. This will be our acid. This will be our acid going backwards, and this will be our base going backwards. So we compare the two acids, water versus hydronium. Well, water is a lot weaker. Hydronium is a lot stronger. And also water versus hydroxide. This is not a favorable reaction at all because water is much more stable than hydronium and hydroxide. And so if we're looking at the energy of this, this is quite uphill. And so you wouldn't expect balls to roll uphill, but we have high energy ones as well. And so if we take, let's say, a billion molecules, then maybe about 4 out of a billion have enough energy to make it up and react. And that's what we see. We see about 4 out of a billion. Well, 4 out of a billion, is that much? No, it's barely anything. But it's something. So typically we would say no reaction, but if we look at it at the finest level, we'd see that there's a tiny bit of reaction. That tiny bit of reaction is going to generate kind of a constant concentration of hydronium and hydroxide. This is what we call dynamic equilibrium. Because as soon as this stuff is formed, hydronium likes hydroxide, and the reverse reaction will take place. But the thing is, you have a bigger water, not all the waters are moving at the same energy. Some of them are going to be high energy, and so what's going to happen is another couple of high energy water molecules will collide and result in this. And so this is just constantly forming and constantly being consumed by the reverse reaction here. And so what we're going to end up with is, it depends on the formation rate. If the formation rate is equal to the consumption rate here, then we hit a state of dynamic equilibrium. And so at equilibrium, we can measure these concentrations. It's a constant concentration. And so at equilibrium, we have a constant concentration. And the concentration of hydronium is 1.0 times 10 to the minus 7 molar hydronium. And the concentration of hydroxide is 1.0 times 10 to the minus 7 molar. And it turns out that the hydronium and hydroxide, when we multiply those, the product is also a constant. And so the H3O plus times the hydroxide concentration is going to be 1.0 times 10 to the minus 14. And we call this Kw, is a constant. Okay, the hydronium is 1.0 times 10 to the minus 7. The hydroxide is 1.0 times 10 to the minus 7. The units here are molar and molar, but K doesn't have units. There's no units for this. So that's what we see here. Okay, now this K is at 25 degrees C because if we change the temperature, that's going to change the number of higher energy water molecules. In fact, it's going to increase the number of higher energy water molecules. So if we increase the temperature, we're going to expect more hydronium and hydroxide. And this is going to change kW. It's going to make it bigger. If we decrease the temperature, it makes it smaller. And so this is kW at 25 degrees C. No units, and it has to be at 25 degrees C. kW changes with temperature. So here's the reaction here, the water equilibrium. And so any sample of water, you take 1 billion water molecules roughly, and about 4 of them will react. So that just gives you an indication of the ratio there. Very little product, mostly all reactant, as we'd expect based on the driving force. Heavily favored toward reactant. So water contains hydronium, which is strong acid. Water also contains hydroxide, a strong base. And so water contains those. However, water is considered neutral. It's considered neutral because the hydronium, when the hydronium and the hydroxide are equal in concentration, we call it neutral. If the hydronium is greater than the hydroxide, we'd say it's acidic. And so this is pure water. Hydronium equals hydroxide. The hydronium equals the hydroxide. This is going to be 1.0 times 10 to the minus 7 molar. This is neutral. In solutions, we can upset this balance. In solutions, we could have the hydronium greater than the hydroxide, like in acid solutions. Even though it upsets the balance of hydronium and hydroxide, this still holds. That is, the hydronium times the hydroxide has to equal 1.0 times 10 to the minus 14. So if the hydronium increases, the hydroxide must decrease in a proportional amount. And so we call this one acidic. And then if the hydronium is less than the hydroxide, then we call it basic. So this is what's shown here. Oh, this is just seeing what the concentrations are. Where do they get kW? They get kW by taking measurements. You can measure these concentrations. You measure those concentrations, and you can calculate what kW is. And so this is just going backwards from kW back to the individual concentrations. And they just took the square root of it. It's the water. All right, so determine the hydroxide ion concentration in a solution in which the H plus is 10 to the minus 5 molar. Is this solution acidic or basic? And so in all solutions, including pure water, this holds. The hydronium ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the minus 14, which we call kW. And therefore, if I want to determine the hydroxide ion concentration, the hydroxide ion concentration is equal to kW divided by the hydronium ion concentration. kW 1.0 times 10 to the minus 14. The hydronium ion concentration is given as 10 to the minus 5. And so I'm just going to do this. I'm just going to do a 1 times 10 to the minus. Actually, maybe I will. We need that 1 for the calculator. In the calculator, when you enter the scientific notation, you have to enter 1 times 10 to the minus 5, not just 10 to the minus 5. Otherwise, you might be off by a factor of 10. So why don't you give this calculation a shot on your calculator and see if you're off by a factor of 10 or if you're right on. You might be able to do this one in your head also, but just see if you could do it in your calculator. Ten to the minus 9 molar. So which one is bigger, the hydroxide ion concentration or the hydronium? Looks like the hydronium ion concentration is bigger. The hydronium ion concentration is 10 to the minus 5. The hydroxide ion concentration is 10 to the minus 9. Therefore, it's acidic. Acidic solution. Solution is acidic. We also have something called pH and pOH and pKw. P represents the power, actually the negative power. Like for example here, 10 to the minus 5, 5 is the power. Actually negative 5, but we take the negative power. 10 to the minus 14, 14 is the power and the negative power. These are power functions. So if we take PQ, where Q is any function, then the math is simple. So PQ is just equal to the negative log of Q. Therefore, we could do different things here, like the power of the hydrogen ion concentration. The power of the hydrogen ion concentration is the negative log of the hydronium ion concentration or the H plus concentration. The pOH is the negative log of the hydroxide ion concentration. And we have pKw. pKw is the negative log of the Kw. And so it just works out to the negative power. If the coefficient is 1, the coefficient is not 1, then a little bit more work in the calculator. So let's take a look at some easier ones. Let's say the H plus or H3O plus concentration. Put that in the square brackets like this. Is equal to 10 to the minus 7 molar. Then the pH is the negative power of this. pH is the negative power, then it would be, the pH would be 7. pH. Let's say Kw is 10 to the minus 14. If Kw is 10 to the minus 14, then the pKw is what? 14. So these are power functions we can do. We can also go backwards. If we're given the pH, then we can calculate the concentration. And so we have some equations that we're going to be using here. Like this. The equations that we'll be using, just write them out, are used to interconvert different things. And so if we're looking at the hydronium ion concentration, we can relate that to the hydroxide ion concentration. We can relate that to the hydroxide ion concentration using Kw. Kw is the hydronium ion concentration times the hydroxide ion concentration, which equals 1.0 times 10 to the minus 14. So we could go either way. We could go from hydronium to hydroxide or hydroxide to hydronium, just like in the earlier problem. We can also go from hydronium to pH, because pH is equal to the negative log of the hydronium. This is log base 10. We can go from the pH to back to the hydronium. Going from the pH back to the hydronium, we use this. We use the anti-log base 10. And so the hydronium concentration is equal to 10 to the minus pH molar. We get the anti-log base 10. The same thing with the hydroxide. We can do the same type of calculations with hydroxide. Hydroxide to pOH is equal to the negative log of the hydroxide ion concentration. And the OH minus would take the anti-log, which is 10 to the minus pOH power molar. It's the power. Then we get the pOH here. Then we can go straight from pH to pOH using pKw. pKw is the power. pKw is actually 14.00, which is equal to the pH plus the pOH. That's what we do. pH is often used to tell you if a solution is acidic, basic, or neutral. If we have a pH of 7, that's neutral. It's acidic if the pH is less than 7. It's basic if the pH is greater than 7. This is the diagram. I just drew it a little bit differently. The pH loop. Well, let's take a look at the problem here. What are the pH, pOH hydroxide hydrogen ion of a 0.01 molar sodium hydroxide solution? So we have 0.01 molar sodium hydroxide. The two ways of thinking about this. One is 0.01 molar sodium hydroxide. That's going to break up into sodium ions and hydroxide ions. We're going to figure out what is the molarity of these. So one thing we could do is we can set it up like this. I have sodium hydroxide here, 0.01 molar initially, and this is going to break up into sodium ions and hydroxide ions. And so I'm going to call this I for initial. Let's say none of it's broken up. It's already going to be broken up. We're just doing this for bookkeeping. Well, for bookkeeping, we're going to say nothing's broken up. And then soluble salts, like sodium hydroxide are completely ionized. So this will be minus 0.01 molar and plus 0.01 molar plus 0.01 molar. And so, this is the change. C stands for the change. At the end of this change, E, we're going to have 0 molar of the formula unit, 0.01 molar of the sodium ions, and 0.01 molar of the hydroxide. And so at the end of this, we're going to just have 0.01 molar hydroxide. And so this solution is going to contain 0.01 molar hydroxide. The sodium ions are not going to affect the pH. Sodium ions are neutral. All right, so that's the hydroxide. So the easiest thing to do is calculate the pOH. The pOH is going to be, what's the power of this? Well, this has 1 sig fig. So we would write this 1 times 10 to the minus 2. And so do you see the power of that? The power of that is 2 point, okay, now we're going to go 2.0, like this. So the sig fig rules are a bit complicated, because here I show 1 sig fig. When you look at power functions, the power functions, everything after the decimals is sig fig. So this only has 1 sig fig here. Anything preceding the decimal is not significant. This 2 comes from that 2 there. So it's not significant. Or we could just go ahead and calculate it. If you take the negative log of 1 times 10 to the minus 2, or the negative log of 0.01, we get this, 2.00. Okay, what's the next easiest thing to calculate here? If I have the pOH, then it's pretty easy to get the pH. What's the pH going to be? Can you do that in your head? 12.0. pH is 12.0. Does that make it acidic or basic or neutral? Make it acidic? It makes it basic. Yeah. pH 7 is neutral. pH is less than 7 are acidic. pH is greater than 7 are basic. So this is basic. If that's the power of the hydrogen ion concentration, then the hydrogen ion concentration of the hydronium ion concentration is going to be 1 times 10 to the minus 12 molar. Here, we did that in our head. We could use the equation as well. Here's the hydrogen ion concentration. Even in basic solution, there's hydrogen ion or acid present. It's just in very small quantities. In basic solution, the hydroxide ion concentration is in large quantity. But we can't get rid of, you know why we can't get rid of hydronium in a basic solution? Why we can't get rid of hydronium in basic solutions is because you can't stop the collisions. The collision is going to happen. There's no way to stop them. So that's one. The same thing, in acidic solution, there's going to be hydroxide ion present. It's going to be very small. So this just shows you concentrations and pHs. Typical pH range is 0 to 14, typically. But we can be outside that range too. If we go outside this range, then things don't behave so nicely, so ideally. So if we're near neutral, we call it neutral, or near neutral. And then if we're close here, this would be weakly basic, this would be strongly basic. pH 14 strongly basic. These are strongly acidic, like pH 0 is very strongly acidic.
What would be an example of something that goes outside the bounds?
Outside the range there, like a volcanic lake. Look at, let's see what the, what would be it? Well, let's see what's in the range here. It's from USGS. So looking in the range, we have battery acid. Battery acid is like pH 1 or 0. Lemon juice is about pH 2. Vinegar is about pH 3. Milk is close to neutral, or just slightly acidic. Baking soda, pH 8.5 or so. Seawater is pH 9. So seawater is pretty basic. Milk of magnesia, pH 10, pH 11. Ammonia, lye is sodium hydroxide, 13, 14. So those are pHs that you see. We can actually go negative pHs. These would be like, well, you can read it here. Negative pH in extremely acidic mine waters. So if we don't bottom out at 0, you know, when we're at 0, that's pretty acidic. But we can actually go negative. Extremely acidic mine water from Iron Mountain. That's in California. California's got really diverse geology. But this is natural water. You know, this is not man-made. Of course, we can make a solution. It's easy to make a solution that goes negative in the lab. Easy. It's easy because this. When you look at the power, what is the, if you have a pH of 0, what is the hydrogen ion concentration, the power of the hydrogen ion concentration? 0. What that means is, if you have a pH of 0, then we're dealing with 10 to the 0th molar hydrogen ion. What is 10 to the 0th molar? 1 molar. Is 1 molar the most concentrated acid you can get? No. Yesterday we saw 11 molar, this is commercial acetic acid. 11 molar HCl is negative pH. Negative. You could just do it in your calculator. Why don't you do this? 11, I forgot what it was. but just do 11 molar H plus. What is the pH? The pH is the negative log of 11. What is the negative log of 11? Yeah. Right. Do you see? You can get negative pHs. Oh, this one, you can put the whole article online. That's good. I'm going to save this one. Call it extreme pH. We have pHs greater than 14 as well. But solutions don't behave so ideally at very high concentration. And therefore, the math we use is more complicated than what I've shown here. It's a bit more complex math to deal with those. And so between 0 and 14, the math works kind of nicely. So that's why your book limits it to between 0 and 14. If they decide to go outside of 0 and 14, then they have to introduce new concepts and new math to you, which is too much. And so this is one of those cases where it was like the single replacement reactions. Do you remember what I said about single replacement? If I limit it to a certain select group of single replacement, then it works perfectly fine every time, right? But if I open it up, then it doesn't quite work. Same thing with this. So we're going to limit it to pHs between 0 and 14. It works okay, but once you go outside that, then this calculation doesn't work so nicely. But unlike the reactions, we're not going to get into it. You can get into it later in a more advanced class. There's not enough time to get into it. Yeah. So this brings up the very common misconception that pH is minimum 0, maximum 14. That's wrong. Yeah, well, that's what lots of people think, including in Chem 1B. I've asked that question, and people get it wrong. But anyway, here's more things. You know, black coffee's fine. You know, blood, slightly basic. More stuff. But the most basic ones, 1 molar. We could have greater than 1 molar. We can have 6 molar sodium hydroxide. 6 molar would mean it's we measure pH using indicators. Indicators are dyes, colored dyes that change color depending on the pH. There's a structural change there. I saw an interesting one the other day. Universal indicator is good, or pH meter. pH meter is good. So let's see if I can bring that one up. I should have looked for this earlier. Really interesting one. It's okay. But anyway, there's lots of other ones that are shown here. We can just take a look.
need is a few drops of universal indicator solution. And we look to see what color the solution turns. Here the solution turns bright red. So we compare that to our chart and see that red corresponds to a pH of 4 or lower. Further testing. It could be a 2 or a 1 or a 3.
Well, anyway, we could use the universal indicator. There's a lab. We aren't going to have time to do it, but what's much easier is to use a pH meter like this. That'll tell us the hydronium ion concentration. All right, for non-integer, we have to use a calculator. Like these ones are called integer because the coefficient's all 1. So we're just looking at the power. But if we have a coefficient that's not 1, we call it non-integer, and then it makes it a little bit more difficult, the calculation. More difficult. And so all we do is we just use the calculator. That's it. So let's take a look at this example here. Hydrogen ion concentration of a solution is 2.7 times 10 to the minus 6. Okay, 2.7 times 10 to the minus 6 is between 1 times 10 to the minus 6 and 1 times 10 to the minus 5. And so this is going to be between pH 5 and pH 6. Where exactly is it going to be? Where exactly is it going to be is we might as well just use a calculator to figure it out rather than to visualize it using logs. And so easiest thing is, let's see where it's going to be. If it were 1 times 10 to the minus 6, then it's so easy. If it's 1 times 10 to the minus 6, then the pH is 6. But let's go ahead and try this here. Well, what we do is actually, I'm not going to write it on the board. Let's look at this. You just plug it into the calculator. This is going to be the negative log of 2.7 times 10 to the minus 6. So it turns out that it's at 5.57, between 5 and 6. 5.57. This has 2 sig figs. Power functions, the sig figs are after the decimal. Power functions are, whenever you see a P, that's a power function. And we count the sig figs differently. The first digit's a placeholder. We know that the power is between 5 and 6. The second 2 digits here are significant. That tells us where it is. All right. Whereas in a normal number, these are significant here. This one's not significant. So if this is not significant, that corresponds to this. And these 2 are significant, which corresponds to that. All right, so that's the pH. Then we can get the pOH using pKw, which is 8.43. And then we can get the hydroxide. Hydroxide is the anti-log, or the 10 to the minus pOH key. Comes out to 3.7 times 10 to the minus 9. So we just plug those into the calculator. We can figure those out. That's from this line here. Okay, we'll look at some problems later to get there. That last reaction, autoionization of water, is what we call an equilibrium reaction. It's a dynamic equilibrium. Lots of reactions occur as dynamic equilibrium. So let's take a look in chapter 18 of reactions in physical processes that occur as dynamic equilibrium. You know, when we have a dynamic equilibrium, then the forward rate is equal to the reverse rate. You know, it might be biased towards one side or the other. You know, in fact, that's often the case. You know, sometimes it's like 50-50 mix. You know, forward and reverse. But sometimes it's biased towards the reactant. Sometimes it's biased towards the product. That's what we have. But the equilibrium is dynamic equilibrium. So we have these double arrows that we show for it. In a closed system, it's dynamic equilibrium. And once we hit the state of dynamic equilibrium, there's no net change. So a lot of this stuff on this slide, I don't really worry too much about. Okay, this is the reversibility of the equilibrium here. So this is probably not the easiest one to see, but essentially we're going to have a dynamic equilibrium between this. It has to be completely closed. The CO2 has to be sealed in there. It can't escape. If the CO2 escapes, then it means it's not a closed system. It's not going to be an equilibrium. So they keep it. But anyway, they're just showing that this reaction is reversible here. That is, in the forward direction, if you take calcium ions and bicarbonate behaves like carbonate. You just knock that extra hydrogen off, form calcium carbonate. This one also forms some CO2, so there's going to be extra bicarbonate there. This reaction is reversible. They're reversing it here by taking calcium carbonate and CO2. Calcium carbonate and CO2 and water are going to form these. So it goes both forward, form a precipitate, and reverse. Consume that precipitate. So this is a reversible. Which side's favored depends on the energetics, which side's more stable. Which side's more favored we call the spontaneous direction. And so what we're going to do is we're going to look at two things. We're going to look at thermodynamics. Thermodynamics tells us the energetics of this, tells us which side is favored. But we're also going to look at something else called kinetics. Kinetics tells us, the speed of the reaction, not necessarily which side's favored or which side's unfavored, but just how fast you expect the reaction to occur. And those are two different things. Normally with thermodynamics, we just wait until the reaction is done. With kinetics, we're interested in how long it's going to take the reaction to be done. And so when we're looking at the kinetics, the speed of reactions, then we look at collisions, and we call this collision theory. So what do we call it? Collision theory of chemical reactions. It's going to be collision. Collisions are going to break bonds and form new bonds, but in order to break bonds, you have to have enough kinetic energy. Not only that, you need the proper orientation. Some things are easy to orient, like spherical things. Other things are hard to orient, depending on the shape. And so to have a successful collision, we need kinetic energy and orientation. The same goes with the water molecules. The water molecules, the oxygen has to hit the hydrogen. It has to be properly oriented. And it has to have enough kinetic energy. And so here's some examples of collisions. This collision looks successful, because the orientation's right, the energy's right, they collide, and break up into product. This one does not look successful. The orientation doesn't look right, the energy might be okay, but the orientation's not right, it's not going to happen. And therefore, this is an unsuccessful collision. The same thing here. Orientation, actually this looks like lower in energy. Orientation and energetics be right in order for it to react. It's collision. Let's follow the progress of a collision. If we follow the progress of a collision, this is what we call a reaction progress diagram here. So we start off on the left here. On the left we have the reactants. On the right here we have the product. So how do we get from reactants to products? How we get from reactants to products is we have to break bonds and we have to form new bonds. And so in going from reactant to product, one, there has to be a collision with the correct orientation and the correct energy. If those are incorrect, it's not going to be able to climb this hill. This is what we call an activation hill. That is, it has to have enough energy to break the bonds and start forming the new bonds. Then it can go to product. And so there's got to be this collision here. Now this is very interesting because overall this reaction is exothermic. But initially there has to be a collision with enough energy. That is, initially it's endothermic here, but it's going to be exothermic overall. Now when we look at the collision here, there's going to be something called a transition state complex, or a transition state. In the transition state, we're transitioning from reactants to products. You can see it's blue, blue, red, red. We're going to go to blue, red here. But in this transition state, bonds are being broken, the blue, blue, and the red, red, and bonds are being formed, the blue, red. And that's right at the top here. You see that transition state? This is a state of high energy here. And so there are some terminologies here that we're going to deal with. One is the activation energy. Activation energy, E sub A, that's the energy required for reaction. E sub A reverse, you know, if we could reverse this reaction, we just have to climb a bigger hill here. Delta E is the energy, it's endothermic or exothermic. In this case, it's exothermic. We're dropping down in energy going from reactants to products. So we have this activation barrier here. This potential energy barrier is a hindrance that must be surpassed for a collision to be effective. And the amount of energy is called the activation energy. And we can see that in action here, like methane and oxygen. Is methane and oxygen a stable mixture? No. But why isn't it exploding immediately?
Not enough activation.
Not enough activation energy. I need to give it a little kick. How can I give it a little kick? I can just warm it up. If I warm it up, then it'll catch on fire. So this is exactly what's happening here. If I take methane and oxygen, the reactant mixture is much less stable than CO2 and water. The problem it doesn't react immediately is because of this hump it has on that hump. Once it climbs that hump, then it's self-sustaining. You know, it generates enough energy to get others over the hump. So anyway, this is a little thing about kinetic versus potential energy. I'm going to skip that. So things that affect the rate of the reaction. One is temperature. Do you recognize this curve? This curve is called a... I'm sorry? No, it looks like a black body curve. But it's not a black body curve. It's the kinetic energy distribution or speed distribution. First time we saw this curve, do you remember what chapter it was the first time we saw this curve? I don't remember the chapter number. I think it was chapter 6. Let me just double check. No, it was not chapter 6, sorry. It must have been chapter 7. No. Chapter 8? No. It was earlier, sorry. It was chapter 4? Yes, it's chapter 4. That's the first time we saw this curve. I must have just written it on the board. It's not in the car. It's also in the gas. What was the gas? What was the other gas chapter? 14?
Yeah, no.
Yeah. 14. Take a look here. It was in another chapter. It's the chapter dealing with kinetic molecular theory. Do you remember kinetic molecular theory? Does that name ring a bell? Yes. Yeah, that's the chapter it was in. Maybe it was chapter 2. But anyway, this is just a distribution. I have a population here. And at, let's say, room temperature, the blue curve, most of the population has this energy. But not all of them have the same energy. you know, there's a small fraction of high energy. This is important for water. You know, in water, you know, let's say 1 billion of them have this energy, but about 4 of them have enough energy and orientation to react to form hydronium and hydroxide. Here. Well, what happens to the hydronium and hydroxide? If I heat up the water, what's going to happen? If I heat up the water, things are going to get hotter. In other words, this is going to shift to higher energies. As this shifts to higher energies, what happens to the fraction?
It's bigger.
It gets bigger. And so this is the minimum energy here, E sub A. And so you can see an increase in temperature means the reaction is going to be faster because
We've gone.
greater number of molecules reacting with enough energy. And so the speed of the reaction depends on the temperature. It also depends on the activation energy. Some things have weak bonds. Weakly bonded things will react very fast. Strongly bonded things will react very slow. Yeah. So the activation energy depends on the bond strength. Well,
Professor, why do weakly bonded things or strong? Is it because it's easier to break apart?
yeah, right. It takes just weak bonds just take less energy to break. It takes less energy to break. Let's say it takes this half as much energy. You're gonna have a lot more. Or if it's double the energy, you're gonna have a lot less. This energy is 262. So the activation energy depends on the bond, but the fraction of high energy depends on the temperature. So we can easily adjust the temperature, but can you make the bonds weaker or stronger? It turns out that for some reactions, you can actually make the bonds weaker. You can make the bonds weaker by using something called a catalyst. A catalyst lowers the activation energy. So typically what a catalyst does is it just weakens the bond. Well, how does it weaken the bond? How it weakens the bond is it uses like intermolecular forces to pull on the molecule itself. As it pulls on the molecule, it causes a tensile stress, which weakens the bond. Inhibitors are things, they're natural catalysts. Some people don't want reactions to go too fast. They want them to go slow, so they'll put in inhibitors to disrupt catalytic action. So this is what happens. This is the same reaction. This is the reaction progress. So here we start off with reactants to this product here. And so normally, without a catalyst, it has to climb this big hill. But if we add a catalyst in there, it weakens the bond enough to make it a lot smaller. But you notice the double hump here. This is just to emphasize that it might not react in the same way it did before. We call that a mechanism. A mechanism. We can see this in this. This is the population energy distribution. And so without a catalyst, with a catalyst, here, the catalyst weakens the bonds. Good thing about catalysts is they're reusable. So once the bond has been broken, the catalyst can find another bond to break or help break. Okay, so catalysts will speed up the reaction. Do I have a picture of the catalyst? No. So how do catalysts weaken the bond? Let's just take a quick look at that. There are different types of catalysts. One of the most common catalysts are biological catalysts called enzymes. And so enzymes are natural catalysts. Natural meaning they're made, but in biological systems. And if you look at the enzymes, they're going to have some kind of structure. This. And then let's say there's a molecule here with a bond, XX bond. And so the enzyme is going to have some kind of attraction to one end of the molecule. And the other end of the molecule. So the enzyme's pulling on the molecule, and in fact it's pulling on this bond. It's going to weaken this bond, making that bond easier to break. So that would be an example of an enzyme otherwise, where there's just some intermolecular types of attractions that are going to pull it apart. And so once that bond is broken, then the enzyme is no longer attracted to the product. So this is going to break free, and the enzyme's ready to catalyze another one. So the enzyme is really weird because enzymes catalyze, it's reusable. So what happens is you consume it, and then it's regenerated at the end. There are other catalysts too. What I was looking for is acid catalysis. So for example, if we look at formic acid decomposition, formic acid is HCOOH, that. Formic acid can decompose into carbon monoxide and water. But this isn't a very fast reaction because what has to happen in order for formic acid to decompose in this way? And what has to happen is we're going to have some intramolecular acid-base type stuff going on. So for example, here, this oxygen is Lewis base, this hydrogen is Lewis acid. We can knock that off, put that there, and put that here. So we get some kind of thing happening, and I'm just doing this in one step, but it probably occurs in multiple steps. So we probably should do it. Let's do it in multiple steps here. And so here the proton gets transferred over to this oxygen. Like this, and it's going to leave this lone pair here. The lone pair on this oxygen. And the formal charges are kind of screwed up because the oxygen has a positive formal charge and the carbon has a negative formal charge here. Oxygen is quite electronegative. So one final step would be something like this, where that goes there, and to complete the octet, another thing goes there, and then we're left with the products here. However, if you do this using some acid in there, the acid could help make the reaction a little easier. And so what can happen is something like this, as a possibility. And so rather than this oxygen here having to vibrate and take this hydrogen out, an acid, it could easily take something like this, the catalyst here. So let's go ahead and attach that, or protonate that oxygen here. Protonate that oxygen, you're going to get this HC double bond. This is our old Lewis acid base reaction. That's going to create a positive formal charge here, which oxygen is not very happy with. And so what can happen is this. this oxygen might hold the electrons off here. Whether it happens just like this or someone like this, depends. So oxygen's not that happy here. So that's going to result in a species like this. Well, this carbon's not so happy because now this carbon has the positive formal charge here, and it doesn't have an octet. So one thing can happen here is, let's go ahead and bring this down here. And then we'll bring these electrons here. So in the final step, we'll regenerate the catalyst here. It's H+. And we'll have carbon monoxide and water. So rather than doing this kind of intramolecular proton transfer that we had over here, it's easier to do it like this. So if it's easier to do it like this, then it's going to make the activation energy lower. Although it's a bit different, you know, we call this a mechanism. The mechanism is a bit different.
So the H+ is just by itself again?
It's just by itself again. And now once it's cycled through, it can cycle through again. And continue to be reused over and over again. All right, what else affects? Concentration affects it. You know, there's another way we can get the reactions to go faster, and that's just to increase the concentration. In other words, the other way to do that is just to keep the temperature the same, but just increase the population. If we increase the population, then we're going to have a larger fraction. So higher concentrations, higher pressures will increase the population, which means the reaction goes faster. That's kinetics. These are things that affect it. This chapter should be split up into two because kinetics is one topic, that's how fast. Thermodynamics doesn't care how fast. Thermodynamics just wants to know what the balance is. You know, the ball is going to roll downhill, uphill, how's it going to be as far as the balance is. And of course, kinetics is going to refer to how fast we establish dynamic equilibrium, you know, the time. This is the time it takes for reaction to occur. And so initially we just have forward reaction occur. But as a forward reaction occurs, it builds a product, so a reverse reaction can start to occur. And eventually, reverse and forward at the same rate. Actually, this is reverse and forward, sorry. Eventually, they'll hit the same rate. All right, we'll take a break here, and then we'll start. During this break, let me pass out the test.